Okay, everybody, so what we have here is I'm going to give you the basics of sample survey principles. We're going to start off by just talking about what exactly are we trying to do here. We've got a population which consists of y1 to yn in a mathematical notation, but that represents capital N values, or a whole lot of values, which you're all aware of. So really it could be the people with their hearts. The Y's are really the reading on those N population values, and we're interested in something about the population. But we've spoken about the reasons why we sample. It will take too long to look at all of them, all the various reasons, it's too expensive, etc., etc. So we're going to draw a sample, and the sample is represented there, y1 to yn, so those are like the people we chose, and say we took their hearts, whatever, and that will be the y1 up to yn. Now, we need to select a sample to estimate the population parameter. So what we're trying to do, there's something, a parameter is something about these values. I might want to know the average value. I might want to know the total value. Okay, so there's something that I want to know about these people. It could be all those y values are, say, values attached to those population elements, and I want to know the average value or the total value, etc., etc. Say y1 is how many farms the first person owns. Y2, how many, or not farms, let's say how many houses, how many rooms in your house, person 1. Y2, how many rooms in person 2's house. So if I add them all together, it will be the total of the population. That will be how many rooms are owned by the whole population, etc., etc. So it depends on what you want to do. But the main thing to remember is that the only you've got your population in a frame. With other words, I've shown you before, it's a big listing. And maybe it's listed by student ID numbers if it's student I'm choosing. Then from this big set, I'm going to, from the frame, select a sample. But remember, the only actual values you have is the sample. You don't have the readings on all the population, because else you would just work with that. So you may be going to then personally go and speak to each person, with other words, to do a personal interview, or you're going to phone them, or you're going to send them an email, or whatever you're going to do, measure, whatever you're going to do. But this is the only, in the end, the set that you're going to work with. But you're blind beyond the sample. So you don't only want to work with a sample, you want to use a sample to estimate something about the population, which you're already aware of. So we have a parameter, and we represent it by theta. That's the thing about the population I'm interested in. I'm interested in, population doesn't have to be people. We've spoken about that. It could be the total, it could be the mean value, or even the proportion that belong to a certain category, and we'll talk more about that later. Now, as an example, suppose that we are interested in finding the total number of children under the age of 5 with parents that work at UKZN. Now, suppose we've got 642 employees in all at the university. Obviously, then your number of people in your population. Hi, everything's fine. Thank you. Okay, so what we have is we have a sample. Now, suppose my population size is 642, and we chose a sample of size 60. We've spoken about different kinds of sampling. That will come later. We know you get stratified sampling, cluster sampling, simple random sampling with and without replacement, PPS, and so on. But however method you use, you chose a set of 60 from the 642. And so that will be how many people are in the sample, and for each of them we want to know in the sample how many children do you have under the age of 5. So to put it in perspective of what I said earlier on, there's 642 people. You don't speak to all of them. You only speak to 60, and you say how many children do you have that are under the age of 5. Each one of those 60 get asked that in the sample. Then we're going to use that information to say something about the whole population. So I know everything about the children under 5 for the 60, but I don't know that for the rest of them. Okay, I think that's very clear. So the question then is, how do we know what number of staff to interview? I said 60. Why 60? Why not 70? Why not 50? So what you need to know is that number 60? How did I get to that? So should I have taken more? Should I have taken less? How do you decide? That's the one question. The next thing you want to know, I said I want to take the best possible estimator. How do I know it's good? What makes an estimator good? What is a good estimator? And then you want to know, is it close to the true value? Obviously, that's what you're interested in, but what exactly, how do we define it? Now, in order to understand this deeper, I'm now going to talk generally about getting into the real thinking about what we're talking about. I've given you an example, and this is to say the population is fixed. How can I say the population is fixed? It's defined by the problem. If I'm interested in how many children under the age of 5 are amongst the employees of UKZN, do you think it makes sense if I say that, if I don't say on a particular, I want to know for as of 30 August, whatever, between 30 August and a certain day, because somebody could have a baby under 5 next month. You need to have a defined period that you're working with, because it also doesn't make sense. Because you want to know how many people, how many children are there with parents at UKZN where the children are under 5, but people are having children all the time. So you've got to say for what period. I'm defining only during this period, whatever. So depending on that, your population will be defined by the problem you're interested in. So it's a fixed thing. There's one population. Think now, what are we trying to do? I'm trying to pick a sample to estimate something about population. If you play soccer, if you're aiming at a goal, because the goal here is to try and get my sample to tell me something really good about the population. So I'm aiming at the population. Imagine if you're aiming at a goal and it's moving around. You couldn't play soccer like that, right? It's a fixed goal, you're moving and you're trying to quick into the goal. That's what you must remember. Your population is fixed, you're aiming at it, okay? It's got fixed parameters. The mean of the population is a fixed number. The total of the population is a fixed number because it's defined for a period, however you said. So your parameter, your theta, is a fixed thing. So whether I'm talking about the total, the parameter of the population, the mean, or say the proportion of people that are employees that have children under age 5, that's a parameter of the population. Say it turns out that if I looked for and I said August the 30th, how many children did you have under age 5? And I asked each of the 60. I could then say 10%, 6 people had children under the age of 5 in my 60. So I could say 0.1 is the proportion of people in the sample that have children under age 5 that parents work at UKZN. Because I say that 10% of the sample, can I now say 10% of the population? If you select it in the right way, you can say near 10% maybe, but how will I know what is good and what's not good? So that is what this is about. But the main thing to remember, these population parameters are fixed. Don't ever talk about E of big Y bar. You're showing you don't know what you do. Because big Y bar is not a random variable. It doesn't have a mean. It doesn't have a variance. It's a single value. Okay? So that is really important. On the other hand, the sample, there are many different samples. There's one population, that population's got a mean, it's a constant. You know, if I pick 2 of you out of this class from the frame of all your student numbers, depending which 2 I picked, if I asked you a question, how many pens do you have in your pencil bag? Maybe if I pick these 2, the average number will be different to if I pick those 2, right? So the mean of the sample is different for different samples possibly. That's why this population mean is a constant. But on the other hand, your sample statistics are random variables. What does that mean? The sample mean, little y bar, is a random variable. You must be very clear on that. Okay? So you talk about the expected value of little y bar, the expected value of the sample mean. makes sense. The expected value of the population, E of this, is nonsense. E of big wild bar makes no sense. Do you understand that? Similarly, the sample mean has got a variance. Why? Because they're different samples. And if I take that sample, I get that wild bar. If I take that sample, I get that wild bar. Another wild bar. So they're different wild bars. So I must know if my sample is good, what does that mean in terms of the variance of a wild bar? That's the kind of thinking you must have. And just as a matter of interest, when you do simple random sampling, if you want to estimate this fixed thing, you're going to estimate the total, you're going to use N wild bar. This will be talking about it. You know, if you want to estimate the population parameter, this fixed thing, you use this random variable sample mean. So the sample mean estimates the population mean. And you can get the total estimated by N times the sample mean. We did speak about that. And similarly, proportion in the sample belonging to a particular category, that little p there, estimates this big P. But the important thing is each of these are random variables. And each of these are constants. Okay, the obvious question then is, what properties should these sample statistics have to be a good estimator? Now, if you go back to the previous page, I've just said these three are estimators of these three. N wild bar estimates that. The first one, that's the estimate of that. The second one is the estimate of that. And the little p is the estimate of the big P. Okay, but how do I know if it's good or not? What does it actually mean? And that is what we're going to talk about next. What properties must a good estimator have? The first thing you must know, and it looks really funny, doesn't it, when I put it like that? What I've done here is I've got actually from the law book, I've indicated that this little red dot there is the population parameter I'm trying to find. It doesn't matter whether it's the population total, the population mean, or the population proportion belonging to a category. You know from what I said just now, your population parameter is fixed, right? There's only one of them. That's the red dot you see in each of those three cases. Now, think of it as three different types of sampling. I did a particular kind of sampling and I did estimation, and each of these crosses, coming up, each of these crosses indicates a sample statistic. What does that mean? It means I drew a sample and I worked out something from the sample values to estimate the population value. For example, this would be the population mean, that red dot. This cross here is one of the samples. I worked out the sample mean and it was that value. Another time I worked out the sample mean and it was that value. So each cross is you know, you get lots of different samples. I said the sample statistic, which would be the mean, is a random variable. So each cross there represents trying to estimate the red dot, and that's the value you found. Okay? So you can see now the different ways. So you can see here the different sample means for different samples, say, think of it like that. It's all over the place. They're all trying to estimate that one. Here, they're close together, but they're at the top there. Here, ideal, obviously. Because now, the main thing you must remember, I'm giving you lots of crosses in this diagram because it's showing you lots of different samples, and those are the estimators, right? But normally, you only have one sample. So you don't normally, because if somebody said, do you want to do method A, method B, or method C, I would say, well, I'm definitely going to do this one because it's always close to the real one, can you see? But how do you know that? You're only going to do one sample. You don't know the real value. So you can't say, oh, it's near the real value, because if you knew the real value, you wouldn't have sampled. You're not going to use a sample and say, is it close or isn't it? Oh, yes, I'll use a sample. Because you're trying to find the population mean, you're actually trying to find the red dot, but you don't know the red dot. So you've got one cross, you this guy, but you don't even know where the red dot is, so you don't know whether it's good or bad. You don't know where the other crosses are that you could have. So that's the whole situation. So what can we say? The different measures, and I'm so sorry it's not, there's something wrong with the projection, because that should show you the top line and it doesn't. I wonder if Oh, no, I can't even change it now. The top line says precise, and you can't see it, but it's unfortunate. Different values of theta hat do not vary too much between samples. So the word precise, if we just think about that, precise says an estimated theta hat is precise. It means there's not too much variance between samples. Now if you look at this, it means different samples give you values close together. Would you say this one is precise? The crosses are all over the place. No, that one is precise, but it's always wrong. That's not very good, but it's still precise. Precise just means your different samples give you similar values. This one is precise, and it's good. But what is the next one? Let's look at the bottom one. Accurate, forget bias one. Accurate says the theta hat values for different samples are close to the real values. Different samples, the crosses are close. No, no, yes. This one is precise and accurate. Can you see? Because precise just means it doesn't vary a lot. The crosses are near each other. So bias. What does bias mean? Theta hat is unfair. That one's definitely biased. Can you see? You're always up in the corner. It's far away, but it's not symmetric around the thing. This is not precise. They're all over the place, but it's actually unbiased because you could be much too big or much too small. So bias tells you whether it's fair. Your dot can be in the middle, but it can be far away as long as you're not more on the one side. Roughly balanced is what bias is. So I can see that is unbiased, but it's not precise. This one is biased and it's precise. It's biased because they're not fairly distributed, but it's precise because they're close together, and that one is unbiased and precise. So, okay, so I'll put the stuff up there for you, and you can read it. As I say, I will be putting this up on Moodle as well. So this particular one is accurate as well as precise. So that's obviously the best one because the values are close to the real one and they also are unbiased. Now if you look at that diagram again, I just screenshotted it. You can see obviously the most desired one is the end one, and unfortunately I'll tell them to fix the data projector, but you're not getting the top line. But what I want to show you is what exactly do we mean, and you must get used to the notation now. Theta hat is the thing that's coming from the sample. Theta is the parameter. So you say, this is the population thing I want, and I'm going to estimate it with this thing. It's the estimate of the parameter. And that theta could be a total, it could be a mean, or it could be a proportion, say in R. It can be a median too, it can be many other things, but that's what we're going to be considering. So when I want to know how accurate it is, that's the accurate. Look at the picture at the end. The crosses are the theta hats. How would I say something is accurate? It means that all those different crosses must be close to the real value. The red dot is this one. These are the crosses. So accurate will obviously mean the average distance, you know, this modulus is distance. It doesn't matter whether it's positive or negative. It's saying this must be small, then it's accurate. The theta hat minus theta must be very small, okay? And how am I going to, so the accuracy measure is to look at this. How far are the crosses from the red dot? Because that's a parameter value. Okay, and what does the word average mean? Obviously, when you're looking at average of distances, you think of how much does it vary. So I'm looking at the expected value of theta hat minus theta. How far is what do you expect? Expect is average. What do I expect the difference between the sample value and the theta to be, the real value? And why do I square it? Who can tell me? What's a square for? Why wouldn't I just take without the square? You know what? Average. If I didn't have a square, would you say if you're far away, if it's a -1, okay, compared to a +2 or +3 or -4 compared to a +1. It doesn't matter how far you are, whether it's left or right. You want to just say, this is the real value and I'm far away from it. It doesn't matter whether it's on the positive or negative side. You're not going to let the negative ones look worse than the positive ones. You get it? The squares, because the sign doesn't matter. This is the real value and I'm far away from it. Whether it's on the left or right is irrelevant. You're not near the real value. If I want, say you want to estimate average income of a group, it doesn't matter whether you estimate it too low or too high. You're far away from the real value. You're inaccurate. That's the important thing. Okay? So, how am I going to measure precision? What is precision? Remember I said precision was variance of theta hat. It's precise if those different samples gave you similar values. So how do you measure how far the theta hat is from each other? You look at the average theta hat, which is E of theta hat, and you say, are they close together? That's just, what is the definition of variance of x? E of x minus E of x minus E of x all squared. You're used to the variance. But what it's really saying is, think of E as expected value. How far on average do the different crosses fall from their own mean? Not from the true value, from their own mean. So if you look at this first picture, the middle picture there, their own mean will be in the middle of those. If you look at the middle picture now here, the red dot, think where E of theta hat will be in the middle of all those little crosses in the corner there. So they'll be close together. The fact that they're far from the real value is totally irrelevant. You see, precise just says, are the values close together? And that's what I said I wanted to do in this course, show you the concepts so that you understand even variance better. This is saying, there are lots of different theta hats I could get. What do I expect? Because I know this is a variable. Do you expect all the different values to be close to their own mean? And that will tell you here, what can you say? That one's not precise. From their own mean, not from the real value. And in the end, remember, these are random variables. Because this is a random variable, this is a constant. This is a variable again. When you have a variable minus a constant, it's a variable. So that's why you put expected value here. This one, theta hat is a random variable. The second one, if you're trying to measure precision, you're going to look whether you can make, what does it look like on average? How much do the theta hats vary from their own mean? And you want the average one. What does average mean? What do you expect it to be? What's the expected value? Okay? So this here, this is a random variable. What is this? E of theta hat is a constant. E of x is a constant if x is a variable. And that's very important to understand in this course because people get mixed up. And they start saying E of a constant. This is a random variable, this is a constant. So random variable minus a constant is still a random variable. So that's why you can take the expected value. But you can't go and put the expected value there because E of theta hat is already a constant. E of theta hat is a constant and theta is a constant. So it'll make no sense for the bias to start looking for the expected bias. No. Bias is a single thing. There's only one, there's a bias. It's the average value of all your theta hats minus the true value, and then you take the modulus of that. Sorry, you had a question.
Square thing, when you see that 235 on the absolute value will be 5
The same as the formula for the variance. It doesn't matter as long as it's consistent across. You're just comparing the actual size of the difference. Whether you always, that's why we do standard deviation, you take the square root again. If you want to know an actual values, but variance definition is that it's taken as a square. The modulus also, of course, would not make a difference, but the variance formula's got the square in, and that's why the standard deviation is a typical average distance, because they take the square root of the sum squares. Right, so as I said here, these two are both constants, so you don't put it here. Think about what you're doing when you do it. What is the deeper meaning of it? So that we call the mean square error. So the mean square error of theta hat, what is that? That's how you're going to measure your accuracy. Your precision is measured by the variance of theta hat. They're the same formulas, E of theta hat minus theta, E of theta hat minus, but instead of a theta, I've got an E of theta. And I don't want you to remember off by heart. It's so easy when you just think of what is it doing. What is the mean square error? If you say, what does the mean square error do? I want to know how close is the sample value to the real value. Okay? So it's going to tell me how accurate I am. Because what does accuracy mean? I've got one sample, and if the mean square error is small, my single sample I know has a value that's close to the real value. You know that. So what is the whole object? If you look at this, I'm going to have one sample and have one theta hat value. I want it to be close to theta, whether it's a little bit too small or a little bit too big, I don't care. It must just be a small mean square error. Because they're one of these, and there are lots of those, but I'm only going to draw one of those. So I want this to be small. That's your main thing. You want to be accurate in your estimation, obviously. But now, never mind, I won't know this value, so I can't just go and work it out. I've got to say, what do I expect? What is the mathematical expectation? How far I'm going to be away? And in terms of mean square error as it's defined there. Precision, on the other hand, has got nothing to do with the real value. It doesn't care about theta. It just says, these theta hat values, if I took another sample, another sample, another sample, do they vary a lot? It's got nothing to do with the real value. There's no theta in this formula. See? So it's just saying different samples vary or they don't. A lot. Now imagine you draw one sample. If I took this sample, the mean is 20. If I take another sample, the mean is 350. I take another sample, the mean is 45. Now remember, I'm only taking one sample to estimate with. I would be really scared to use that method because different samples having a big variance. It's just by good luck or bad luck which one you get. So if they're all over the place, it's a big problem. Like this first one. It's not precise. You always want precision. You want it to be so that the values are close together, and ideally, like in the last picture there, close together and close to the real value. So you want it to be balanced. So really, if you want to be accurate, you've got to be unbiased. They mustn't be on the one side, and they must be near each other. So that is your accuracy definition. Then the next thing is we've spoken about bias, we've spoken about precision, and we've spoken about accuracy. And I said the mean square error will tell you how accurate you are. Your variance of your theta hat will tell you how much they vary. So that tells you about the precision. And your bias tells you whether it's fair or unfair. But there's some relationship between them, as I said in the previous one. You can see here in the last picture, it's very precise, okay? You can see it's unbiased, that last picture. They're near each other, so theta hat's got a small variance, this is small, and this bias is 0, because it's unbiased. Unbiased, you know from even second year you learn E of theta hat is theta, or E of beta hat is beta, means it's unbiased. But you haven't really in your head thought what it means. It means there are lots of beta hat values or beta values, and I want them on average to give me the right value. That's what unbiased is. Now, what is the relationship between accuracy, precision, and bias? Or similarly, between mean square errors, how we measure accuracy. How do we measure, how do these unbiased measure up? What is the mathematical expression for them? And that is the next one, because you can see in that picture at the end, to be accurate, you've got to have precision, close together. In other words, I want the mean square error to be very small. I want the variance to be small. I want the bias to be 0. That will be the ideal. But there's a mathematical expression for that, and we can easily show that. Mean square error, this is the thing you want to have small, obviously. I'm only going to have one sample. I'm going to work out a theta hat. What do I expect will be the difference, the squares there, between theta hat and theta. Theta is the population value. Theta hat is my sample value. Do you think it's going to be big? How will I know? I want that to be really small. Okay, obviously. The formula is, it's the variance of theta hat plus the bias squared. And I can very easily prove it to you, but I want to demonstrate the concept rather. What is this saying? This is saying I'm going to have a single sample, I'm going to work out a theta hat. If the mean square error is small, it means there's a mathematical proof to show, even though I've got one sample, it's going to give me one theta hat. I can expect this thing to be small, theta hat minus theta, expected value of theta hat minus theta squared. For that to be small, it means the mean square error is small. That actually is saying your theta hat is near theta, isn't it? If E of theta hat minus theta is nearly naught, it's small, it means this thing is small. I can expect my theta to be near my theta hat. So I've got one sample, it's going to give me one theta hat. Mean square error low means my sample theta hat is near theta because that would make that expression small. You get it? So that would be a very good thing. Now they're saying you'll get a really good thing if you get this small. But this is equal to that plus that. So for this to be small, the mean square error, you need a small variance and a small bias, isn't it? Because what you must remember, they're all positive. A variance can't be negative. You know the formula for variance. Can't be negative. Something squared. Can bias squared be negative? No. So I want this small, obviously. This can only be small if they both small. So good sampling means my single theta hat I could expect to be close to theta, mean square error is small. But that means both those are small. Ideally bias is 0 means they're not there. Your bias is 0 means that they're beautifully symmetrically distributed and the variance is small. It means they're close together. Can you see now those pictures? Now, if you go back to that story, the three pictures at the top, think of that one at the end which showed the red dot with those little crosses near each other. No matter which cross you pick, which sample you've got, will give you one of those crosses. All of them, the crosses are close together, variance is small. It's beautifully symmetric, there's no bias. That's small, that's fine, that's good, that's small. You can expect if the sample you pick will give you one cross, it will be okay, it will be close to the real value. Do you understand that story? Sure you get it? And here's the mathematical proof in the case of T hat. If you feel like doing it, you're welcome to, and I'll gladly explain it to you, but it's not going to be in your exam at this stage. So I'm just putting it up. Last year it was, and far longer than this, by the way. I had some 4-page theorems, so if you want to go there, I'll gladly do that with you. But I want you to really, this year, I'm pushing to understand the basic concept. So do you get it? So I hope you're with me. But that is how, what does this say? Mean square error T hat. If you look at the previous one, I spoke about mean square error theta hat. So it just means I'm estimating. Hat means estimate. I'm estimating theta when I have mean square error theta hat. What have I got here? Mean square error T hat. All I was trying to do is estimate the total of the population. And I went through the proof and I show it's the variance plus the bias squared. And I said mean square error theta hat is variance of theta plus bias squared. So what it's saying is you take the variance of the sample statistic and you add the bias of the sample statistic, square it, and so on and so on. But now I'm going to give you another example. Suppose we've got 30 students in the Stat 240 class. We want to estimate how many pens a typical student in the class has with him on a day based on sampling. So 30 students, I'm going to pick 5 people, come forward and empty your pencil case, let's count. And I don't feel like doing it for all 30 because it will go crazy. So I've got 30 and I pick 5 from the 30. So I just use my calculator or however you want to do it. And suppose those are my people. First person had 4 pens. The second one is one of these guys that just stares at you and never writes anything. He's got no pens. There's another guy next to him, his friend. He's also got none. Person 4 has got 3 pens. Person 5 has got 3 pens. So this is my sample. I picked 5 people. And I said, how many pens have you got? Show me. And that's how many they had. So between that lot, the average for the sample, I added together the wild values and I got 10, 4, 5, 6, 7, 8, 9, 10, divided by 5 people, on average they're 2. So now I'm saying on average there are 2 pens per person. 2 pens per person. No one had 2, by the way. One guy had 4 noughts and 3s. It doesn't mean that you'll get a number. And just as a matter of interest, while we're on this topic, often I get something like, let's suppose it was 11 over 5. Then it would have been 2.2. Can you have 0.2 of a pen? What does it mean if the mean? Suppose you have children, they say, you'll see some of Stats SA says, on average in South Africa, there are 2.3 children per family. And you might laugh and say, this is hilarious. What would you do in that case as a matter of interest? What would you, if it's whole numbers and you work out the mean, you can get a fraction like 11 over 5 would be 2.2. What does it mean, 2.2 pens? What would you do? Would you make it 2? What would you do? Huh? Okay, who will tell me? Anybody, put up your hand. Just shout out. What would you do with 2.2 pens? Would you make it 2 or would you leave it as 2.2? Okay, you'd make it 2. Now let's suppose you find the average number of pens is 2.2, you make it 2. In another class, I do the same experiment in another class in computer science and I find it's 2.6. Let's say no, it's 2.4. One is 2.2 mean, the other class is 2.4. But I record it as 2 because they both, I'm rounding down because you can't get 0.4 pens. But now they're both the same, but they're not the same. Because now I want to say which class have got people more pens. I would have thought computer science, they're working on their computer, they don't bring pens. But I want to say computer science has more, but when I took the 2.4, I just recorded it as 2. You never ever, when you find means of whole numbers, round off. Do you know how you read it? You say 2.2 is between 2 and 3, but closer to 2 than to 3. 2.4 is between 2 and 3. It's closer to 2 than 3, but I know it's more than 2.2. You always read it. You can get 1.7, child. It's between 1 and 2, but it's closer to 2 than 1. So if they work out per country, the average number of children per country, you don't just have 1, 2, 3. You might find in Sweden it's 1.1. And in France it's 1.6. They can't make them both 1 and 2. They leave it as a fraction. But in your mind, you say between 1 and 2. It's between 1 and 2, it's here on average. But don't ever round off numbers like that. Just as a matter of interest. Okay, back to the story. I had 30 people. How many pens have each got? I brought 5, chose 5 people. I could have chosen them and lots of different kinds of sampling. But I ended up with those 5 guys. They brought their pizza boxes and on average they're 2. Okay? So now what can I say next? Ooh, I messed up there. So what I wanted to say is that for this particular, just to get used to the notation, theta hat is an estimate of the population parameter. What am I trying to estimate? The average number of pens of the 30 people. That's the big Y bar. So my theta is Y bar. I'm estimating population mean. I estimated with little theta, which is your sample mean. I worked out the sample mean, you know it's 2. Okay, you're all used to that. So my sample mean is 2, but would you say now, because there are 2 pens on average for these 5 people, that for the 30 it must be exactly equal to 2 as well? Well, first of all, you wouldn't say it because, you know, even between them, they were varying. One guy had 4, 3, 0. So just because your sample's got a value doesn't mean that the population's got the same value. How do we work with that? So we have a point estimate. The sample mean is 2. But what can I say now about the population mean? And that should be very familiar to you. What we try and do, we sample using whatever method, okay? We then use the confidence interval to say, we know a 95% confidence interval, you take the parameter plus or minus 1.96, the square root of the variance of the parameter, not of the original population. You say, if I want to know, I can't just say the sample mean is 2 pens on average per person in my sample and therefore it's 2 in the population. No, I say the real population value is the sample value, but I know it's going to vary a bit, so I go the sample value minus the confidence interval sample value plus the confidence interval. It was another run from where you But by the way, you understand what I mean. You go either way because you know you can't be so accurate. And it's really important that you think about what you're doing because our sample statistics are point estimators. They're always in the center of the confidence interval. Because you take the sample statistic and then you add the piece and you subtract the piece. That puts your sample statistic in the middle. You go a little bit that way and a little bit that way. How far must I go? I say that's my sample value and I say, oh, I think it'll be near there. Okay? So, your sample statistic is always your estimator, your theta hat, is in the middle of your confidence interval. And then you say, I'm 95% sure it's in this area, in this particular interval. The important thing to note, however, is this variance. I find that really interesting. You know why? I'm using this to estimate that. Okay? I'm using my Y bar to estimate in this particular example the population mean. But I've got, take the value from the sample and you say I'm 95% sure it's in a particular interval. How far must you go depends on the variance of this thing. Isn't that obvious? If that Y bar is varying a lot, you better go far away to be 95% sure. To me, that is so, because you know, up to now, what have we done? We prove theorems, we learn theorems, but you don't think deeply about what you're doing. If you want to be 95% sure, you better link how far you go to catch 95% of the possible values with a variance. Because if it's varying very little, you can say I'm 95% sure it's in this little interval. Because no matter which sample you get, the Y bars are very similar. Every sample's got its own Y bar. And they're all very similar. The variance is small. So you can be 95% sure if that's your sample value. Different samples don't have lots of different values. The real value is somewhere near it. But if your Y bars are varying a lot, and you get a sample value here, you better have a wide confidence interval. And that's why this has to obviously be part of the confidence interval. And that's a very important key point. Make sure you understand that. Because it's really, and the next thing you must know is that different ways of sampling are going to give you different expressions here. There's not just variance Y bar equals this. If you use simple random sampling with replacement, there's a formula. If you use simple random sampling without replacement, there's another formula. There are lots of different formulas. And you're going to say, well, which one is going to make my confidence interval small and so on? Because I'll give you an example of just in general confidence interval. If I say, for example, I want you to estimate for me the number, let's take the previous example, the number of pens. I want you to give me 95% certainty. What is the average number of pens that a person carries in his bag in this class? And I'm going to pick two of you and I'll get a sample and I'm going to estimate. Without even picking people, I will tell you 100% confidence interval. It's somewhere between 0 and 500. Isn't that true? It's true. I'm 100% confident. That's absolute nonsense. You want to say I'm 95% sure it's between 2 and 3 or between 2 and 5. If you don't have a narrow confidence interval, you're talking nonsense. Because you can just make it wide and be 100% sure. So that is the important thing that you should think. How can I work so that my sample value, which is the Y bar, gives me such a small variance that I cannot talk nonsense? If they say, like the 2-liter bottle of Coke, what's the average amount of Coke put into the 2-liter bottle by the machine? You don't want to say somewhere between 1.1 and 4. I mean, it's just nonsense, the bottle. If you say that in your company, they'll fire you. You want to say, on average, my sample gave me, it should be 2 liters, it came to 1.94, but then that's the middle of your, when I take, say, you work out from the variance 1.94, it's somewhere between 1.96 and 1.92, Now you're saying that whole confidence interval doesn't include a 2 litre. It should be 2 litres. So it's putting too little in, from first year. So your confidence interval around that value is tight. And it doesn't include the 2 litre. Now you know you better adjust that machine. So you don't want wide confidence intervals. This is always going to be in the middle of your confidence interval, your plus and minus, and this has to be small. The whole object of sample survey, how can I make that variance 50 to small? Okay, that is all. Now I think from this exact